Welcome to our next unit where we're going to be taking an in-depth look into the basics of bonding. In this chapter, we're going to be taking a look at a lot of really key pieces and key vocabulary. First of all, we're going to be looking at the difference between covalent and ionic bonding. And once we start talking about ionic bonding, we're going to take a look more in depth about how ions and why ions are formed, and even what is an ion. And after that, once we know that those ions come together to form a compound, a little bit more about ionic compounds, how we name them, and more what they look like in a larger structure. So at this point, I'm hoping that you have a better understanding about not only the structure, but kind of the function and forces that are at work on the inside of an atom. That's going to be really key as we move forward because as we bring two atoms together to start to bond, those forces determine absolutely everything about how the larger compound, how we see it in real life, actually really behaves. Now, the most important force that we're going to talk about in this chapter is electronegativity. And yes, we did talk about electronegativity briefly during our last unit, but now it is in the forefront. So just a little refresher about what electronegativity really is. We'd kind of talked about it in a couple of different loose ways. In general, we kind of talked about it as the ability of an atom to grab electrons and keep electrons toward itself. If it's grabbing other electrons, generally speaking, it's doing that through a bond. And again, we kind of said that you can kind of use the term electron greed here, although I want you to be very, very careful with using that. It's not an academically kind of approved way of talking about electronegativity. The official real definition is the ability of that atom to attract other electrons through a bond. How strong is it? What kind of a bully is it to try and, steal a baby's candy, I guess. Moving forward, electronegativity is actually on a numeric scale. We keep it simple, a 0 to 4 scale. 4 being a very high electronegativity and 0 being a very low electronegativity. So the higher the number, the more that atom is going to want to pull electrons toward itself. Now, we often can actually see this in context with the periodic table. Here's an example of what I mean. We'll have a periodic table, and instead of having the customary atomic numbers and average atomic masses, we'll instead layer it with the electronegativity values. Now you can see the highest is all the way in the upper right-hand corner with fluorine, having the highest number of 4.0. Notice that the noble gases are missing. Their electronegativities are essentially 0. Some of them actually have an electronegativity, but that's mostly we're leaving them off because they tend not to bond in any way, shape, or form. The lowest is going to be on the extreme opposite end of the periodic table. We're seeing this one as being cesium, but we probably know that the lowest is going to come up as francium, with the lowest electronegativity on the periodic table. So don't forget that trend. As you go up and to the right, your electronegativity will tend to increase. Now, we need to understand why this force exists. So this is some new learning in this particular unit. There are two atomic forces at work here that can explain every single trend. The first force is called electron shielding, and the second force is called effective nuclear charge. I'm going to take a few minutes to explain both of these to you. First, let's take a look at electron shielding. Here is a planetary model of just a simple atom. You can see it has two shells of electrons. I like to almost call those shields, although nobody else calls them shields, but it kind of can be helpful to understanding what electron shielding really is. Now you can see that the electrons are going to be attracted to the nucleus. The nucleus has all of those positive protons, and around the outside you have all of those negative electrons. And what do opposite charges like to do? Attract. And what do like charges do? They repel. So you can see that there are little red lines on here showing that the electrons repel each other. Now notice very carefully that those little red lines are not drawn between electrons on the same ring. So when we talk about electron repulsion, we're not necessarily talking about the electrons on the same ring repelling. This is ring-to-ring repulsion. Now, The outside electrons are almost as equally as attracted to the nucleus as those inside of electrons, except for one key thing. They're being blocked. The inside shells literally shield the outside electrons from being able to attract to that nucleus as well. They're blocking them. You got to get through that line of defense to try and get to that beautiful positive center. This is electron shielding. So the more shells that an atom tends to have, the more electron shielding there will be, blocking the valence shell from the nucleus. Now, these then tend to be less tightly held because they simply don't have the ability to break through all of those internal shells to enjoy the nucleus. Now, let's take a look at one more specific example. These are some noble gases, and I'm just going to pop up some planetary models for you. Here's helium, and we're going to go straight down the noble gases now. So here's neon. It has an extra shell. Argon has yet another shell. Krypton and xenon. Now take a look at all of the different levels of shields here, and notice also what happens to the size of the atom. It simply has to get bigger because it has more shells. But the more shells that it has, the more shielded the valence shell is from the power of the nucleus. It just can't be as tightly held. The second atomic force that I'd like to describe to you is effective nuclear charge. In other words, how effective the nucleus can be at attracting its own electrons. Now, I kind of liken this to something that we may have learned about in biology. We always hear about the mighty mitochondria being the powerhouse of the cell. Well, if the mitochondria are the powerhouse of the cell, then the proton is definitely the powerhouse of the atom. The proton has a lot of power to pull. That's a lot of alliteration there for my English friends. Now, we have on the screen here two different atoms, two different planetary models. Now, they come from the same row on the periodic table, so they have the same number of shells of electrons, but they have different numbers of protons, neutrons, and electrons. Now, beryllium simply has less mass. Oxygen has more mass. But notice in this picture, oxygen is drawn as being smaller than beryllium. But wait, oxygen is heavier. Why is it smaller? It has more stuff, yet it's smaller somehow. We need to be able to explain the why. So again, think about the protons being the powerhouse of the atom. More protons, more pull. Which nucleus is more effective at pulling the electrons around it? Take a look at beryllium. Beryllium has 4 protons. Now take a look at oxygen. Oxygen has 1, 2, 3, 4, 5, 6, 7, 8 protons. 8 protons is more power. In fact, it's double the power of the beryllium. So the nucleus of oxygen is more effective, more powerful at pulling in its own electrons. And what you're seeing in the image is literally what happens in real life. The electrons are so attracted that the shells shrink. It's almost like shrink wrap on the inside of that nucleus. So the more power, the more pull, and the shell will kind of just decrease in size. Let's take a look at a larger image where we can kind of see this more in play. Now we're going to be looking straight across a group here. We're going to go from lithium, carbon, nitrogen, oxygen, fluorine, and neon. Now notice one very important thing as we go across this group here. They're all from the same row of the periodic table, therefore they all have the same number of shells of electrons. That means they have the same level of shielding. There's only one shell of electrons on the inside. There's only one core shell of electrons shielding the valence shell from that attraction. Now, yes, there are more electrons filling into it, but it really doesn't matter. You can see that that shell is kind of the shell. It's not going to be any bigger. It's there. But what does change, and this is the most important part, are the number of protons on the inside of that nucleus. More protons, more power, more pull. As you go across a row on the periodic table, although you're adding in an electron, you're also adding in a proton. More protons, more power, more pull. Neon in this group will be the smallest of the atoms, whereas lithium in this group will be the largest. It's because it has the least number of protons in its nucleus, given the same number of shells, and therefore is the least effective at pulling in its own electrons. So again, neon is most effective and lithium is least effective. So when we're taking a look at the periodic table, it's important to kind of keep these in mind now as we're explaining other trends, because now this can be linked to atomic size, atomic radius. It can also be linked to ionization energy. You need to think about the power of the nucleus pulling in those electrons. So let's just review one more time. In a top to bottom argument, remember, every time that you go down one row on the periodic table, you're adding on a shell of electrons. So in a vertical argument, if your atoms are aligned vertically on the periodic table, you tend to use a shielding argument. And as you go up the periodic table, you'll tend to have less shells and therefore less shielding. Those electrons tend to be a little more tightly held to that nucleus. In a side-to-side argument, as we go across a row, you have the same number of shells, but what is changing is the number of protons. So as you go from left to right, you tend to increase the number of protons and therefore experience a greater effective nuclear charge. Now the symbol for that is Z sub EFF, or ZEF for short. Again, that's a symbol or shorthand that you can use when you're writing and talking about effective nuclear charge. So the location on the periodic table that experiences the least amount of shielding and the greatest amount of effective nuclear charge tends to be up where fluorine is. They tend to have the most tightly held electrons. And the opposite side of the periodic table, down by where francium is, tends to have the most weakly held of all of the electrons. So now keep this in mind. Again, the most important force in this chapter is going to be electronegativity, but these two forces can be used to explain all of the other associated invisible periodic trends.